Hello, everybody, and thank you for joining the Solving the Trillion-Dollar Problem, Splunk at Murex. Today's presentation is a quick overview about who am I, a very quick overview about a little about Murex. We're going to talk about the problem we had at Murex, the limitations we had, and then we're going to talk about how we brought in Splunk as a third-party tool into Murex to fix the problems that we had. And then I'm going to go through some test cases, specifically the trillion-dollar problem, millisecond analysis, and so where's my test. So just some real-life examples of where we actually use this technology. Okay. So very quickly, that's me. My main job for the last 12 years is a performance tester, a non-functional tester, and I'm also a Splunk developer. Okay, 4 years ago, I started developing Splunk. So what is a non-functional tester? So imagine you get a developer to make you a GUI with two buttons, button A, button B. And he comes back, but he's forgotten button B. There's no button B. That's a functional issue. Functionally, it doesn't exist. Now, a non-functional issue is if you press button A and the CPU goes crazy, and the Java goes crazy, and the network I/O goes crazy, and the whole platform collapses. Basically a non-functional issue. So my job is when big banks take Murex, because Murex produce financial software, they install them into big banks around the world. They spend maybe 6 months or a year implementing this very difficult financial software. And on day one, when 200 traders hit the system with e-trading and users hit the system, I'm the guy who has to do the stress testing to make sure that when they turn the key on their new toy, it doesn't break and the bank don't get really, really angry at Murex, basically. Okay? So I'm the non-functional tester. So about 4 years ago, I brought Splunk into Murex to help with some of the problems. This is very quickly where Murex is based worldwide. The major hubs are in Paris, New York, Singapore. Paris, we develop Java and C. Dublin, we develop Java. In Beirut, we also develop Java as well. Now, very quickly, I have to explain what Murex does because I need to explain what Murex does so you understand the problem we fixed. So Murex basically creates software that goes into trading rooms globally inside big banks, investment banks primarily. That's broken into three main parts: front office, back office, and risk management. So the front office is when you see the guy in New York, in Hollywood, trading with a guy in Singapore. And he's on the computer, and he's pricing that trade, and he books that trade. That has to be done on a software. Murex provide that software, okay? That trade then is alive and goes into what they call the back office, okay? So the back office is where they match the trades, and they settle the trades, and it moves on to the accountancy side. And then the final stage is the risk management. An average bank in London might have 500,000 live trades. Every day the markets move. Every day you have to recalculate all the finances of the world on your live trades, because what's a good trade today is a bad trade tomorrow. And you might hear the term hedging coming into place. You hedge your bets. Effectively, this is what it is. A good trade today is a bad trade tomorrow. You buy the negative of the trade yesterday, and you mitigate any potential loss or potential gain. Okay? So, what is Splunk? Now, people who don't know what Splunk is, it's a big data tool. Okay? It simply has the ability to take in any machine data. So what's machine data? It could be logs, it could be anything. The Murex application pushes logs out. So it pushes out, say, hours and morning logs. It pushes out timing logs. It pushes out GC logs. The systems, the servers it's sitting on, they're pushing out CPU logs. They're pushing out network logs, okay? So it just takes all this data in. So when you're running a big performance test like I do, I have to stress this. I have about 9 servers trying to break Murex. Because what I want to do is I want to break it before the client breaks it, basically, okay? So I have to make sure, I have to try and push this as hard as I can. So what we found was the tools we had were good, but we needed better. So specifically what I'm talking about today is TPS tracing, which is a Java trace that we invented inside Murex, okay? So we invented this tracing protocol. It's a light performance tracing tool. It times the method, the class.method, okay? So for example, you make hello world, and hello world pops to the screen. You want to know exactly how long that took, okay? Because you have to now time every class.method that you think is sensitive inside the Java code. And you want that to produce very, very quickly. So for example, I have a method.y. It's taking 5 minutes. Say it's a trade insertion, way too long. Minutes, you get your trading system will get replaced. You need to be in the milliseconds, okay? So I go to the developer and I say, hey, we need to look at this. So I would normally go to a Java developer and say, this is the problem. So he can't really look at method.y because normally in Java code, method.y calls method.b. And effectively you get a situation is on the x-axis here is time, 5 minutes, and the y is measured time. So you have 5 minutes there, it comes down there, but inside that, you've loads of these little 50 millisecond calls. And if we look at the table, method.y is called once, but method.b is called 6,000 times. Now functionally that's fine, no problem there. It should be called 6,000 times. But the performance 50 milliseconds is way too long. So now the developer has a target, because I need to get that 50 milliseconds to 2 milliseconds to bring down the overall 5 minutes, okay? So it's kind of real-time performance. Now why is this important? Well, you say it's only a timing log. I mean, surely JProfile can do this. Well, this is real-time logging. This happens in real time. So it happens not just in production, in client. This is all at Murex when we're doing development life cycles, but also in the client and prod. So for example, you develop something here. Your developers get used to seeing this kind of tracing. They put the tracing in a product development. It goes through the client testing. A big client says, hey, I want that new module. So you put TPS tracing in the new module, and you get all this tracing coming out. Then the client goes to UAT, and then in production, maybe there's a crisis here or a crisis here. Let's hope never here, but sometimes there's problems here. But what happens then is the FTP, the log drops back to us, and we can see exactly what's happening inside the code. And it happens in real time as well. So it just shoots out. Now what is it? Well, any developer in Murex can put the @traced inside any class. And what you're going to get then is a file produced in the logs directory called tps timestamp.tps. And inside the log is JSON. And the JSON will have, I look for 4 basic things, as simple as start, end, method, class. We produce a lot more data, and sometimes in other situations we need it, but specifically for the raw timing, I need 4 things. And it's quite simple. But we produce millions of lines of these data. So what was the problem? Well, the problem was 7 years ago, a major London bank needed super fast performance. And we were very, very far from that. So we had to work very hard. We had to develop TPS tracing. Now the tracing produces, say, in that case, maybe 1,000 lines, 10,000 lines. But what happened in the company, TPS tracing became very, very popular. Everyone saw the power. So this is really good. We can time everything we do. So TPS tracing was started put in everywhere, every class TPS tracing, and the logs were coming out the back end of the Murex application, okay? The problem with that is a TPS report is a PDF. It takes a long time to make these. You have to run the maths, like 100 million lines of TPS JSON tracing. You run the maths, it could take 2 hours. Like, you don't have 2 hours to wait. You want it dynamically, you want it now. So introducing Splunk. So we brought in Splunk to fix this problem. And also with a PDF, you can't zoom in. Well, you can, but you have to run another command. So you're constantly running reports, so it's a problem. So I'm going to show 6 5-minute videos today of illustrating what we developed in Splunk. Now, we developed this in Splunk. The Splunk didn't come like this. So there you can see the classes. So now Splunk has taken all the data in, and we display all the classes and all the methods of this. This is like a 5-minute test, very basic 5-minute test. X-axis is time, okay, 5 minutes. Y-axis is measured time, logarithm in the milliseconds. So 10, 100, 1,000. And now we have the ability that you can hover over any class.method very, very simply, and you can see to the millisecond exactly how long each class.method took, and are you expecting that, okay? And at the end, you can get the fully quantified method there. So you can see all of this took an average of 800 milliseconds. It's called 15,000 times, and all the maths that you could possibly want, because you're doing product testing, or maybe you're debugging a performance problem. What also we can do is we can zoom very quickly. So now we can click on a selection, and as I said, we can go into the millisecond analysis if we want. So we can click, you just zoom on selection, and it drives right in. And again, we can zoom in again if we want. Now what's nice is when you change the viewer up here, the maths changes here. So you might want to disregard the start of a test. Just look at a certain point. The point is it's dynamic. But again, developers always want to see the JSON. So you click on this, and again, you get the JSON straight out the back, because you might want one property here or not. So you can never go too far from the actual JSON tracing as well. You have to keep the developers happy, the Java developers, okay? So we developed this with the Java developers. So how is Splunk installed at Murex? What's the architecture? So we have one major box, about 30 cores in this box. It's a pretty powerful Intel chip. chips. We have a situation when we have about 5,000 Unix machines inside Murex. Any one of these machines can be hosting multiple Murex environments, either from client A, client B, client C. We've developed a way inside that any developer can go Splunk my environment.sh, and straight away it uploads its data to Splunk. The whole point was to make something really, really easy, really, really quick, so that you don't have a situation where a developer has to import this, do 20 steps to see the data. Like it's just one click. And then that's live. Any testing he does in that environment, he can now see instantly in Splunk. Or you have the situation where clients give us log drops. They're having a UAT crisis, having a SIT crisis. And we FTP, and then again, we upload to Splunk. So again, the data just flows straight in, which means any Murex user can see the data, and we can get the analytics that I just showed you there. So we have a very open system that can now look at any test and development environment across the entire platform of Murex, or we can take in any logs from our clients, and everyone can see the data that's happening. Because what was good in UAT might not be good in prod. What was good in development, suddenly it's disaster in production. And we need to understand why. So we keep a record of maybe 1 year inside the Splunk infrastructure. So a more detailed look at that, because people wanted more detailed architecture, is we have multiple servers, and they push on to what the Splunk call forwarders. This is what Splunk terminology is. Inside the green box is basically the Splunk architecture. The forwarders push on to a main index, and this is where you need to train Splunk that if you're taking a TPS log file, you need to train, this is a TPS log file, it's JSON, you need to take it in like this. If it's a GC log file, you say, well, this is a GC log file, you need to treat it like this, okay? Then we, as Murex, we developed data models, and these are like indexers in Oracle to make it faster. So you can access the indexer if you want, but if you get to the millions and 100 millions of lines, you need a data model. It makes it much, much faster, okay? This then pushes on to the dashboard XML. So when I showed you the GUI interface, this is the code we developed. Splunk give you a toolkit that you can develop, say, a drop-down box, and that's fine. But they give you a toolkit, but you have to really develop the dashboard. And it's like C, it's just a big long line that goes down, okay? So it's not really object-orientated, it's more of an old-school C programming is how it works. The dashboard drives the searches drive the drop-downs or the pie charts, and that drives to the end user there, okay? So this is a general architecture of Splunk. I would suggest mainly in most places. The code looks like this. It's kind of like a HTML with embedded SQL. So and as I said, that just kind of drops all the way down, okay? So what does the code look like? So we're doing product development, we're doing testing, and we came up with the phrase, if you graph it, they will see it. Because what we noticed was, say I'm developing a new product, a new report, and I tell the developer, okay, I need you to develop this new report. And he goes, okay, fine. But functionally, he can do it. But non-functionally, he doesn't have a KPI in his head. He doesn't know if he develops this, it's non-functionally going to pass. And it's very difficult sometimes to give a developer this KPI. So what we're finding is that if they look at the average or the means, say you developed a test and it took 5 minutes, and the average was 800 milliseconds for a class. There's 800 milliseconds here for this particular class, the master class. He might go, that's a pass. But if you graph it, very obviously it's not a pass. It's a 5-minute import. It started at 500 milliseconds and it finished at 1,200. There's obviously trending here going upwards. There's obviously a major bottleneck in that code line. In a 5-minute test, it's going through the roof. What's it going to be like in an hour test in production of a major investment bank? You'd be getting phone calls at 3 in the morning. That's what will happen. And the team will have to scramble to, and this is what does happen in the past. We're hoping we get over these problems now. So a quick video on that. So this is trend analysis, where you can just see the problems. So again, as I said, so 1,000, 2,000, 3,000 here. The x-axis is time, and you can zoom in. And now you can see, well, which is the guilty class at method, because they're all not trending upwards. Only some are. And this will help the developer to decide, well, which is trending upwards in a better way. So it's all about helping the developer to get in. So we can see again, okay, it's 800 milliseconds. Now, on another topic, we can see we have a big peak here. And I go, well, that's 3 seconds. That's really big. I want someone to look at this. So what you do is you zoom in, and you go, yeah, it's really big. I need Anne or John in development to look at this. This is the problem. Now, what I don't want them to have to do is reopen Splunk from scratch and click, 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 and do 20 clicks to get to this point. I want to be able to save this with what we call a Splunk ID and generate a URL so I can email them that. So I create soft test, and it saves it on the x-axis or the y-axis of time. And we developed this inside Murex. So Splunk, this wasn't natural to Splunk. We developed this. And you can put in the, in this case, index was removed. This is actually the problem of why it was trending upwards. So, but more importantly, I get this URL. So this ID 777. Now I can put that in an email and say, click here. Jack or Jill, can you please look at this? She puts it there, and within 10 to 20 seconds, she's looking at the exact point I said to look at. She doesn't need to open up Notepad++, doesn't need to go through all the log files that I went through. It took me an hour to get to this point. Why should that person spend an hour to get to the same point? Bang, there you are. And then they can start digging. So that's an interactive dashboard. So that's not a screenshot. That's an interactive dashboard. And that's the idea, that you increase your productivity of your discussions with your testers and your developers. So it's called Splunk ID. Now, as I said, Splunk is good. It gives you tools, but you must develop on top of these tools to make this work for you. It doesn't all come naturally. Okay. So the Splunk ID is quite an easy concept to explain. The standard graph that everyone uses is CPU, time on the x-axis, CPU on the y. Splunk ID, you just go down the z-axis. So client Z, client X, Y, Z. Because I have 100 live environments and I have 1,000 log drops from clients. So I have to, knowing that what time is no good, I must also know the time and the test data. Okay, very simple concept, a bit more difficult to implement in Splunk, but that's what we did. Okay, so then with this ID, we're able to do any testing, tag any test, email any test, put it on the wiki, and make the whole system really, really quick and easy to use. And it was all about making the system easy to use. This was a big thing we had. Okay. So, how did this work for us? So the $1 trillion problem, this is a very Hollywood title, okay? I'm aware of that. I have to explain two more concepts. So the first concept is, what is a clearinghouse in the financial world? And when you understand this, I'm going to then go on to more. So in the 2008 crisis that we all remember, one of the main problems that came out of the crisis was called a liquidity crisis. Okay? Now that meant banks stopped lending money. Now why did banks stop lending money? Well, let's go back to the example. Trader in New York trading with Singapore. Suddenly, Singapore bank actually collapsed. Now, trader in New York is owed money from Singapore, but Singapore is gone. The bank is gone. So now he's like, oh, well, how much money do I have? How much did he owe me? And this proved to be very difficult for banks, amazingly so, to understand very, very quickly how much cash they had in their banks. And this was, everyone's like, I'm sorry, no one could understand how banks didn't know this, because their systems weren't built for this. Their systems were always built to go forward. It was never built for this. So no one predicted this kind of crisis. But why do we care? Well, because banks didn't know, they couldn't lend money to businesses. So the economics of the world had a major problem. Businesses need money on a daily basis, okay? So without money coming in daily, businesses simply have a major problem, and therefore the economy of the world has a major, okay? So the regulatory authority comes along and says, this can never happen again. So we're going to reuse this concept called the central clearinghouse. So again, New York, Singapore, and in the middle, a clearinghouse. So what is the clearinghouse, and why would banks use it? Well, quite simply, if a bank in New York is trading with a Singapore bank, the trade's actually, that's called bilateral trading. They're going to go through the central clearinghouse now, okay? Effectively means that if a bank, Singapore, collapses, New York still gets paid by the clearinghouse. So New York is happy. I still get paid, okay? Yeah, of course. Why wouldn't I use these guys? If they use a clearinghouse, it's cheaper. If they go bilateral trading, they have to keep a certain amount of equity aside. If they use clearing, they keep less equity. They have more money. They can do more trading. Banks like this. And the most important thing at the clearinghouse is there's one location where you can see how much money all the banks have. And this will stop the liquidity crisis, hopefully, ever happening again. So this is what was brought in. Murex have one of these clients, one of the biggest clients in Europe. They were live, they were happy, but because clearing as a financial was getting more and more popular, everyone was clearing now. The system wasn't able to keep up with the amount of throughput they were getting from all the banks. So they said, Murex, we need a lot faster. So we said, well, how fast? They said, well, we need 60 position updates in 1 second. So that's 17 milliseconds for one trade into one piece of critical part of code inside the Murex application, which was developed in Dublin. So we said, oh, okay, let's have a look. And we have about 2 or 3 months to do this, okay? So when I was working with a guy, John Rafferty, he was an English gentleman, I said, John, do you know how much these guys clear? And he goes, no. I goes, John, these guys clear 1 trillion USD. And he's like, wow, they clear 1 trillion in a year. And I said, no, John, these guys clear 1 trillion in a day. That's how much these guys push through this system. So when this project landed on my desk, I was like, you've 3 months to get this to go faster. There's like no pressure, basically, right? So this is a big client, right? So this is as big as you can get. And in fact, since we won this contract and since we're still live, they're now clearing 4 trillion a day. How big is 4 trillion? The US national debt is 20 to 30 trillion. Not say only, but just to give you an idea, that's 12 zeros. Like it's an enormous amount of money flushes through these systems. So we went to work, okay? So the last concept I'm going to introduce here. So I've introduced, we can time the code. Now I need to introduce garbage collection. Now, you're probably a lot of Java developers here, and my garbage collection is okay, but I don't have a PhD in it, because you could write PhDs in garbage collection. So I'm going to briefly introduce what is garbage collection. Garbage collection is the way Java manages the memory, okay? Not all garbage collection is what they call stop the world, but some of it's called stop the world. Stop the world is the stuff we hate, right? Because in performance, if I'm doing a calculation, A plus B to equal C, okay? And that takes 7 milliseconds, I'm happy. If a stop the world that takes 10 milliseconds happens in the middle of that, it takes now 17 milliseconds for that trade to get through the system. Now that's a problem. Now what happens if the stop the world is higher than 10 milliseconds? What happens if it's 100 milliseconds? What happens if it's nearly a minute? Disaster. So it's fine in the minute game, but if you're in the millisecond game, it's not fine. So we had a situation where when we did a basic test, we saw something that we never realized. We were trying to figure out why our results were so bad. So we were at 99 milliseconds average with high volatile peaks. And we're like, why is this so bad? So we're trying X, we're trying Y, we're kind of going a little bit crazy. And then when we overlap the green, which is the trades going in, with the stop the world garbage collection, we get these exact matches. So the green is the trade trying to get through, and the purple is garbage collection stopping the world exactly at those times. So you can see all the matches, match, on all the big peaks. So it became obvious, oh my God, the stop the world garbage collection, primarily in the power new section. The current market sweep in the old generation was kind of coming in, but primarily in the power new section was causing the problem. So let's have a little video on that. So this is the TPS tracing. I've stripped it down to just the raw minimum. These are just trades entering the system, okay? Maybe a 10-minute test. The average is 99. Now we need 17. This is the target. So we've 2 months. We've 2 months to crack this problem, okay? So we get together developers and testers. So we can see we're getting peaks of 500 milliseconds. We're getting peaks of 50 milliseconds. Everything's too high. It's all too high. So then we develop, as I said, it doesn't come naturally, but you have to start thinking outside the box a bit. We develop, well, let's overlay the garbage collection. Let's quantify it. So 46% of the time was spent in stop the world garbage collection. Huge. Like absolutely huge. Like this is a disaster, okay? And then if we come down here, we can zoom in on that and we can see the graph I just showed you, okay? So we can see there's a trade going in, 700, there's stop the world, 600, right beside it, exactly on it. So it became obvious to us, in some cases, stop the world garbage collection was a problem. Now I'm going to fast forward to maybe 2 months' time. Now we did some Java fixes inside the code, some cloning problems we had, and then we also did a lot of functional fixes. So we removed heavy mathematics we didn't need to be doing, okay? So these problems are often solved in multiple attacks. So now we move on to 3 months later, and we can see we managed to get the overall math to stop the world right the way down, which is great, okay? And then we can see now, this are the commits, and we can see 14 milliseconds to 16. So this is like right the way down. So this is after some GC garbage, some optimizations functionally, and in the code level. So now we've hit the target we need to hit, basically, nearly 17 milliseconds. So everyone was happy. So we got together developers, we got together testers, we made a team, we ran tests every night, we produced Splunk IDs, we worked as a big team, high pressure, push. Management wants to know, is it fixed yet? And then eventually we got there in the end, which was a great relief. Now I've put in 2 slides just in case you download these slides and want to see. These are just the mathematics we kind of use of how we quantify these things. So there's the sum of time over GC, et cetera, et cetera. And the next slide just kind of illustrates the before and the after, and this is kind of how we did it, okay? So I'm going to move on now to what we call use case 2. Now, use case 2 was the developers were using the classic XY axis and they were happy. But what they did find is that when they're debugging one problem, say one trade took 10 seconds, it wasn't good enough. It wasn't giving them what they needed to see. So let's have an example here. So one example, this trade took 10 seconds. And the whole thing here is about 10 seconds long, okay? So the master class.method is 10 seconds, and these are all inside that class.method, okay? So one guy calls the next, calls the next, calls the next, calls the next, et cetera, et cetera. So what we said was, okay, let's flip the graph. Let's make it a Gantt graph. Is it easier to see? And it turned out to be a lot easier. The master class here is still taking maybe 10 seconds, but we can see much clearer that this calls this, which then calls this, et cetera, et cetera. And we get this kind of left to right. You'll see it now when the video plays on, going down of how each class calls what. So we're looking for the problem. Why is it 10 seconds? And then all of a sudden we stumble upon the most obvious one that everyone shows in demos. It's hitting the DB. It's like DB, 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 DB. Well, this should all be in cache. Why are we hitting the DB? It's a trade insertion. Like we warmed the caches. They shouldn't be going near the database. But it becomes much more obvious when you're kind of clicking over. As I said, then it goes left, down to right, and it finishes there. Okay? So that's the 10-second starts, and it finishes over there. So this is like a Gantt chart zoom that we created. And we just found this to be very useful. Our developers like this a lot, in fact. So let's give another example, sequential versus parallel testing. I go to developer, product development, and I say, hey guys, we need to do a test of an import. And they say, okay. So the sequential import is 700 milliseconds, and the store existing is sending it to the database, okay? And that's 73 milliseconds. And it looks something like that, okay? So we can see the big line, it takes 73 milliseconds. You go right down to the millisecond analysis here, and you go, okay, fine. But what happens if the client wants to run 15 imports in parallel? Okay, can this code line handle parallelization? And sometimes developers haven't developed that way, they haven't thought about that, but it's inside the non-functional tests. So we say, well, let's give it a go. So when we tried it, we got like a surprise, good and bad news. So the good news is 700 seconds went to 2 seconds, so 3 times slower. It's not bad, it's okay, 15 times import. But no surprise, the 73 milliseconds went to 1,200, so that's 17 times slower. Now that's a DB insertion. And then of course the developer goes, oh, well the DB input is all sequential, that's not parallelized. So you go, okay, but what happens if I try that by 100? Like, is that going to push this out then? And he goes, well, probably, yeah. And then we have to go back to business and say, well, what are the chances we need to do this import by 100? Now, Splunk isn't going to fix these problems, but it just brings it to your attention. It says there might be a parallelization problem in that code line if the client chooses to go to a certain point. Do you know, because you can run non-functional tests forever, and people will like you if you catch things, but if you waste 3 months, they hate you, okay? So you have to be careful that not to fix everything, but you can highlight the problem and say, look, there might be a problem here if we do this. The second last video to show you is called the trace analyzer. So again, we get all these traces, say, from a client. We turn on what we call the trace analyzer. They pull one trace out because we have a parent-child relationship inside the TPS tracing. We click on it, and all the parent's-child associated to that will come straight out. So what we did was we clicked on commit. We can see it's 100%, okay? But that's here. But we can see other things happening in parallel as well because we're on all. So if I click parent and child only, I only see the parent and child. Or if I click all, because it's a multi-threaded application, other things are happening at the same time. So it could be happening on a distributed system. The TPS tracing is coming in. So you have 100 JVMs pumping out tracing non-stop. What I missed showing you there, this is all the code that's running in parallel, for example. Okay? So one class.method, how much parallelization is happening there? Well, 6-to-1 ratio is what's happening in that particular class.method. Can your box handle that? Are you able to handle 6 times that? I mean, these are questions you can ask. Because if that was 50, it's like, well, I'm only running on a 10-core box. Like my ratio is 1 to 50. There may be something wrong here. Okay? So these are all concepts we developed to help our developers to kind of get right better, faster code, basically. Now, the last point I'm going to talk about, well, not actually the last point, sorry, the last use case. It's called, so where's my test? Now, remember, I'm a non-functional tester until I became a Splunk developer. And I could often go home and I would have 5 binaries to test, 3 properties, and I would tee them all up in a big Unix script, okay? And each binary would come in and come out, and each property would come in, and I would run maybe an hour test, an hour test, an hour test. And I come in the next day, and I have test 1, test 2, test 10, okay? The problem was, we only had an Xaxis with lots and lots of lines on it. It's very difficult to know, well, where's test 9, test 12? And very easily, you end up looking at the wrong test or give the wrong Splunk ID to the wrong developer, and he's looking at it, and then he goes, this isn't my code. And then everyone gets annoyed. So we had to develop a way inside Splunk for a very simple overhang. It looked simple, but it was more difficult to develop, that you could identify the test easily. And not just the code, but what's the harness doing. So you stop a harness, you reboot Murex, you start your CPU monitoring, you clean out the logs. You want the test, every test to be exactly the same. There's no point running a test after test if the components of the test are changing, so therefore you can't quantify if it's a good test or not, okay? Okay, so a quick video on that. So again, this is a 2-hour window, okay? We turn events on off. So we can see export test. It started at 11 o'clock, finished at 12. It's an hour and a half. But now you can hover over each part and say, okay, this is the master of the test. Stop, clean, start. Okay, so how does test stop? Stop script, so you're stopping the harness, you're sleeping, etc., etc. And then finally you get to the actual test. What are you actually testing? You're testing an import. And now you can click on that. And instead of opening Notepad++, you get the logs or the errors that came out the back end. Because often what happens is that if it fails, you have to go to Notepad++, FTP the files, which file was it, etc., etc. But now you can relate each of this very, very quickly to a log file. So there's no more opening Notepad++. I mean, I like Notepad++, but I spent way too long in it, opening file after file, or telling someone it's on, the problem is on line 22,000 million, and can you help me look at it? So the conclusion of the Splunk TPS view. Okay, we had a problem. The problem was we needed to view millions upon millions of lines of data quickly. We can get log drops of up to 250,000 lines of data from a client activity. So the PDF report was useless, okay? So now we've developed a way we can do that 100 million in about 10 seconds, okay? So when we upload that, it indexes, and after it indexes, it's just ready to use. The tester can use it, the developer can use it. It's super fast and super quick. It's web-based. Anyone inside the Murex platform can now use this super fast tool to bring up its information. So it could be a UAT crisis, a production crisis, or it could be a production test, or a product development test that's happening, okay? So the idea is we have to keep thinking, okay, number one, it has to be fast, but it has to be usable as well. Like developers have to engage in this, okay? The next problem we had, we need to get Splunk data into Splunk quickly. As I said, there's no point telling a person to do 20 things to upload data, okay? That's useless. You need to tell the people it has to be quick. So we developed the widget, the .sh script, and it just attach your environment, and your data is sent instantly. And within 4 or 5 minutes, depending on how much backlog of data you have, it's accelerated, and then you can see it, okay? And that's the type of usability, because what we had to do was we had to bring a full end-to-end system. There's no point me developing nice dashboards if people can't get the data into it. So we had to develop a full end-to-end system that would quickly run the data in. Okay, we need to overlap different data sets. Now, this is what we showed in the $1 trillion problem. We overlap the TPS tracing with GC, but you can do that for CPU. You can do that for anything you want. Okay, so you have to decide what do you want to overlap. Okay, and it's open to you. But the more you overlap in different screens, sometimes the bottlenecks you see that you never thought were possible, and things that aren't exactly the same time, that you thought, well, why is that happening when this is happening? And then you investigate more. So it's all about making everything, understanding all your machine data coming in, and bringing it in, and then kind of putting it on an axis. We had to show, how can I show my colleagues quickly what I'm looking at? Again, to make it human. You send an email, click here. That's it, one click. We live in the one-click world. If it's 2 clicks, people aren't interested anymore. So it has to be like 1 click, and then they see your solution. They see the problem at 1 click. That's what we needed to bring. Well, that's what I designed anyway to bring this up. The team is quite small. There's only 2 of us in Murex at the moment, and I introduced this maybe 4 years ago, and we developed the majority of this work in-house. So what's next? This is the last slide now. What's next for Murex? So we've got some very good. What I'm showing you here is one silo of one dashboard. We have about 7 or 8 dashboards which are completed and done. Okay, so this is just one silo of one dashboard that we've done. We've done other logs, GC, MX timing, etc., etc. Okay, we've done very similar things. So this is just one silo because we don't have enough time to show you all the silos. Okay, so this is just one silo that we used. We developed this. We're thinking of developing the Murex Splunk app. Murex Splunk is like your phone. You download apps, right? Splunk works the same way. So whatever we develop inside Splunk, we can literally just give that to our clients. So because the Murex platform is producing data, right? So it's like just passing the telescope to them and saying, "Here, look through the telescope." It's the same. It's the same. The data is the same. It's just they don't have the telescope. Now banks spend a lot of money analyzing in investment bank world. Banks would have a lot of trading software in some of the banks, multiple softwares, and it's a big business of all this data coming out, and they spend a lot of money analyzing it. So what we're thinking is, what we're going to start trying is, well, what if we develop an app, and what if we give it to the client? Let's see how that goes. So we're starting to think about that. So we've over 300 major investment banks in the world. The global monitoring system. So again, I showed you one dashboard. We're thinking of making one that will monitor the entire platform. Okay, the heartbeat, we're calling it, just to give an overall health of the system. Okay, so we as Murex could be installed on 20 servers distributed. So it's a lot of machine data pumping out there. Okay, and like anything could go wrong, and you need to know in real time, because if you don't know in real time, traders just lose money. Traders, if there's one thing that gets financial software removed from an investment bank, is kind of instability and bad performance. Like clients, they spend so much money on this stuff, they just throw it out, they get the competitor in. It takes time to implement, it's difficult because the mathematics are quite complex. But like, so you have to be very careful of stability and performance. That is obviously there's more, but this is what I'm concerned about, because I'm the non-functional tester. I'm the guy who kind of does the big testing before they go live, okay? And then the last one, Murex is becoming more popular inside. Now this is a human story as well. So the human story is, I brought this in 4 years ago. And like any new technology, you take in the demo and you try the demo and it works a little bit. And then you need money, because you need to buy an enterprise license. So this costs money. Murex pay for this. So the human story is that you're constantly showing to people it's worth value. And of course you're getting asked questions about elk, and of course you're getting asked, well, why don't we do this? Why don't we do it? Because everyone else knows the answer. But they're not doing the work, they just know the answer. Do you know what I mean? So you're always getting this kind of pushback, which is fine, but you have to manage it. You have to basically instead of going for the goal, just take the low-bearing fruit. Show that any new technology, not just Splunk, show that it works. Show that you're fixing your day-to-day work to your manager, and he says, oh, that's really good, yeah. So don't go in with this big demo that's a 4-year plan, forget that. Go in with just, I have a demo, and this is what I did, and then I won one battle after another. Luckily, say the $1 trillion problem came along just at the right time, that we were kind of ready to handle it, so that the problem came in just at the right time, and then everyone knew that we used Splunk to fix the big clearinghouse problem, and that really helped. So that was a big battle that we won, and then from there things started going on and on and on, basically. So it's becoming more popular at Murex. And now my job basically is, I've kind of done the Java development. My job now at Murex is that I go from team to team looking at their data, fixing their problems, and making dashboards, basically, which is great. So that's generally what I do now. So I go along, I understand technically their problem, I ingest the logs, and now we create these dashboards on the system that I've built that can just take all the data in. Okay, thanks for listening. Hope that made sense. I'd say 5 minutes or 4.5 minutes for questions, if there is any. None. So the question is, how much of the technologies are open source?
Yeah.
Oh, sorry, go on again. Yeah.
Yeah. So, how much of those technologies are open source?
Unfortunately, none. Okay, so Murex as a platform is not. I thought you were clapping again. Murex as a platform isn't, because it's a financial platform. We sell this to clients. The Splunk is Enterprise Edition, so you must buy Splunk. You get a free license for maybe 3 months or 6 months, and then you use it. And then they're very good. They help you a lot. You know, if you have a problem, they help you because it's in their interest. Okay. TPS tracing was developed in-house at Murex. So it's a distributed Java.class.method, but again, it's in-house. It's not open source at the moment. So unfortunately, none is the answer. It was a problem that I had, and I had to fix it with the tools I had, basically. Okay? So sorry, I wish it was more open.
I have one question.
Shoot.
As you are a fanboy of Splunk,
Yeah.
I would like to know if did you consider another solution before choosing Splunk, such as Elastic, something like that?
Yeah, no, I mean, that's a good question. And I get asked that a lot as well. And I have to give a very UN answer to this. Because effectively, I was at a test conference, Eurostar, 5 years ago in Dublin. And this gentleman showed, he was monitoring 50 machines and he had performance problems. And I asked him, what did you use? He used Splunk. So the next day I downloaded Splunk and I started to test it. And I very quickly got very good answers that I wanted. I was like, wow, that's you know, it's relatively okay. Murex does have ELK as well. Like there are developers who do develop in that technology as well. So what I try not to do is start a war internally between the two technologies, because it's important we work together. Now, I personally haven't tried these technologies. So I can't say they're bad or good. I actually just don't know. You know, and I'm not going to say Splunk is king, because maybe, like every technology, you know, Sybase is good at one thing, Oracle is good at another. You know what I mean? Like there's always kind of like a give and take, depending. But for my particular case, Splunk worked quite well. So yeah, we do have ELK inside, or forms of it, but I'm not using it myself. Effectively, my job has very much become a Splunk developer in the last 2 years specifically. Yeah. Okay. One more question here.
I was wondering what was the machines that you were using for the Splunk servers, and what was the cluster that you were using to be managed to use this kind of volumetry?
No, the machine is an Intel chip. I mean, it's in terms of, it's about 3 gigahertz, and it has maybe 2 CPUs, and it has, I think the cores are 16 cores in each CPU, approximately. One single machine, yeah. And the forwarders, just to rewind, the forwarders, just to go back to the architecture picture. Oh, this might take a while. The forwarders can exist on that one machine. So the forwarders can exist. No, it's on the next one. Sorry. So yeah. So the forwarders can exist on the main machine, or they can exist on where the developer has his machine. Okay, so it's kind of like if we have kind of client sensitive inside a secure zone, like we can't have the forwarder on the main Splunk machine. We have to have the forwarder inside the secure zone, and it's only pushing out timing logs, so it's fine. It's not like we're breaching contract, and it's what I see. You have to remember again. The human story is, I couldn't go to my boss and say, hey, I need 20 big machines that are going to cost 100 grand each or 20 grand each. That's how much a machine costs. Like I had to be very, very careful to have one machine and prove high value, low cost. So all the time I'm thinking this, and it's taken maybe 2 or 3 years to really bring that into, everyone's now thinking that way as well, that we are bringing good value at low cost, basically. Does that answer your question?
Yeah, thank you very much.
No problem, yeah. 20 seconds left. Okay. Is that enough? Everyone's all right? Thanks very much for coming. Thanks for listening.